Okay? So circular motion, when something travels at a constant speed along a circular path. Not a constant velocity, because direction is always changing. Okay? What has to happen in order for circular motion to occur? An object must always be changing velocity, which means there must be a force that is pulling on it. Now, here's the next part of that. Which way does that force pull? This is the part that throws people. Because right now, I imagine a lot of you are picturing that tape flying off in a straight line, or you're picturing the last time it was really icy and you turned a corner too fast and your car slid. And it slid out of the corner, okay? That's another perfect example of Newton's first law, by the way. And if you take a corner too fast and pound on the brakes, and then you do what most people do, panic, pound on them harder, okay? All you do is obey Newton's first law. And instead of turning the corner, you slide in a straight line along the corner. Okay? Next time it gets icy, try it somewhere safe. Okay? Like an empty parking lot. But it's totally true. Okay. What keeps you in a corner? What lets you turn? Friction. Think about it. You slide out of the corner when it's slippery. Yeah, when it's icy, because there's less friction. It's friction that allows you to turn. Okay? All of those forces, friction, this string, they're all pulling the same direction towards the center. If something is going to move in a circle, a force that is directed towards the center of the circle must be acting on it. That's why it's constantly changing direction. It's trying to go in a straight line, but there's a force that keeps pulling it back in the circle, okay, and not allowing it to go in a straight line. Okay? That's why the moon orbits the Earth. Okay? If the Earth wasn't here, the moon would want to go in a straight line. But the Earth pulls on the moon. Okay, and keeps it turning all the time, keeps it moving in a circular pattern towards the Earth. So can gravity act as a centripetal force? Sorry, I didn't use that term yet. Centripetal force, that's a center-seeking force. Centripetal means center-seeking, okay? It is any force directed towards the center. Now you're probably hearing that word, centripetal, and thinking Coderre is pronouncing that wrong. Because you're all thinking centrifugal or centrifugal. And people are thinking that right now. Centrifugal is not right, centrifugal is. Okay? There's no such thing as centrifugal or centrifugal force. Okay? Centrifugal means center fleeing. It would be a force pulling the object directly out of the circle. Okay? And no forces do that. Okay? What there is, and what makes something leave a circular path, is inertia. If the force is gone, the object will leave the circle on a tangent straight out of the circle. Okay? Everybody with me on that? Now, some new terms here. Period. Not the thing we end a sentence. Okay? Period is the length of a cycle. Okay? That is the general definition of period, the length of a cycle. Okay? So when we are talking about an object moving in a circular path, the period is how long it takes to make that circular rotation one time. Okay? That would be in seconds most of the time, unless you're talking about planets orbiting the sun, and then it might be longer time periods. Certainly we could express the length of Earth's orbit in seconds, but it's a pretty big number. How long is the Earth's period of rotation? Nice. 365 and 1/4 days. Most people just say 365 days, and most people are wrong, because it is in fact 365 and 1/4 days. Why? That's why I have a leap year every 4 years. Okay? You've got to make up for that extra quarter of a day it actually takes the Earth to go. Okay? It's not a perfect quarter, it's a little bit off, but every once in a while we have a year that comes in a few seconds late. It's a good count for it. Straight for sure. Okay, Centripetal velocity is simply how fast the object is moving in that circular path. Okay? Now, if I have this tape, and it's on a short radius, okay? How fast is it going? Fairly fast, okay? Now, faster or slower? It looks slower, right? Okay? Takes longer certainly to go around, doesn't it? Okay? But it's, we're going to do the math of this later. I just want you guys to visualize it again. Okay? The amount of time it takes to make this rotation is much less. Agreed? Okay? This rotation takes a lot longer, but it's also a lot farther. Right? This orbit is a lot bigger than the first orbit was. Okay? What we have to think about is speed. How many people have ever been on a merry-go-round? Okay? Where is it hardest to hold on? Outside or in the center? Outside. Way harder to just hang on the outside because you're moving faster. Doesn't look like it, but you are. Okay? Moving faster. Okay? We're on the outside. On a merry-go-round, guys, it doesn't matter where you stand. It takes the same amount of time to go around once. Agreed? Okay. So, on the outside, you're going farther in the same amount of time. You have to be going faster. Okay? If you're having trouble holding on, take a step towards the center. Okay? It'll be much easier to hold on. Okay. All right, so uniform circular motion is the motion of an object traveling at a constant or uniform speed on a circular path. Okay, so you can see there that little plane that's like the roll of tape here that I had, okay, going around and around in a circle. Okay. All right. Now, we can see that the length of these arrows are equal, okay, but the direction the arrows are pointing is always changing, okay, and that's what we were talking about. The velocity is always changing, so the object is always accelerating, but it's moving at a constant speed, okay? Weird, but true. All right, so sometimes it's more convenient to describe circular motion by specifying the time period it takes the object to make one revolution, okay? And again, that's the period, okay? How long that time takes. So we can calculate the speed something is moving at by using this formula. What does 2 times pi times r calculate? Circumference. And big T stands for period. So really, this is just that. Would you agree? I mean, the circumference of the circle is the distance the object travels. Okay? The period is the time it takes for it to go around one time. This is just V equals d over t applied to a circle. Right? So it's not a terribly new formula. When you're doing this on your calculator, should you use the pi button or 3.14? Pi button, definitely pi button. Good question.
So the question if you're going to get the perimeter of a circle in centimeters, would you do dd equals v equals d over t?
No, I mean, no, you'd use this, okay? Because this is the distance, right? The circumference, or the perimeter, is the distance traveled by the object. I'm just saying, all this formula really is distance divided by time. Yeah? I'm not saying diameter over time. Yeah, in case I was confusing there. Okay. So V equals 2 pi r over t. So if we're looking at this formula, okay, 2 times pi times r over t, as the radius gets bigger, V should get bigger. Yeah. If t remains the same, r's on the top, right? Okay. If t doesn't change and r gets bigger, V should get bigger. Okay. And that's what we were saying with the merry-go-round. Okay? If you're on a merry-go-round, it's harder to hang on the outside of the merry-go-round because you're going faster there. R is bigger, but T is the same. Okay? It doesn't matter where on the merry-go-round you stand, it takes the same amount of time for it to go around one time. So you have to be going faster on the outside. All right, but it'll take more force to hold you there on the outside than it would in the middle. And I'm going to show you some examples of that that are fun. Okay, yes. So what we've seen there is, okay, obviously radius can affect speed. Okay? We're going to do a little lab activity on that shortly, okay, next week. But radius certainly does affect speed, especially if period doesn't change. Now, most of the time, okay, if things are not connected, then as the circle gets bigger, the time to go around it also gets bigger. Okay? A merry-go-round is an exception because it's a fixed circle. Okay? And so the relationship isn't perfect, right? If radius goes up, period tends to go up a little bit too, but in general, velocity goes up. Okay? Period doesn't increase as quickly as radius does. Okay? So they don't perfectly offset each other. Right? Another application of this is a tire balancing machine. Okay? If you've just recently had your winter tires put on, or you're getting that done soon, it's that time of year. Okay? When they put them on, they need to make sure they're balanced. Okay? The process by which tires are made is not perfect. They essentially pour liquid rubber into a mold, let it cool, and then pull the mold away, and there's your tire. Okay? That process doesn't always perfectly distribute the rubber. So you might have certain parts of the tire that are a little heavier than other parts. Okay? Same with your wheel. Okay? The process by which wheels are made is also not perfect, okay? And they have to be balanced. If not, what will happen is you'll have one part of the tire or wheel that's a little heavier than the rest, and it'll start to chatter. Okay? It'll vibrate. Anybody ever been in a car when they get to a certain speed, it just does that? Okay? Your tires or wheel need to be balanced. It either means the tire needs to be balanced or the wheel's bent. Okay, something might be wrong with it. And what you do is you take it to the tire shop and they throw it on this machine, which just spins it really fast. The machine is spring loaded, so it can tell when the wheel starts to chatter, and it can locate the heavy part. And then all it does is stop it when the heavy part is on the bottom and tells you to put weights on the other side. Okay, so I don't know if you've ever seen this, but on some tires you can actually see on the outside little weights that are clipped onto the tire. Now they actually usually stick them on the inside of the wheel. Okay, so they put these weights on the inside of the wheel, and that helps to balance the wheel so that you don't get that happening. Okay, you can also get it to happen if you drive through a bunch of deep snow, and snow gets stuck on the inside or part of your wheel, and then you start going faster. There can be enough weight from just the snow stuck to one side of the wheel in order to make the tire get out of balance and chatter again. Okay? So what we're going to do is we're going to look at that formula and see if we can calculate how fast the outer edge of the wheel in this example is moving. So we have a wheel of a car that has a radius of 0.29 meters. So we know what R is. Okay? And it's being rotated at 830 revolutions per minute. Okay, so that means it goes around 830 times in 1 minute. Okay, the formula I'm trying to use is this. It contains period, which is the amount of time it takes to go around the circle once. I know this thing goes around the circle 830 times in 1 minute. So can I figure out how long it takes it to go around once? Okay. What we call this is frequency. Okay? Period is the time for one rotation. Frequency is the number of rotations per time interval. They're the inverse of each other. If you look on your formula sheet, you'll see this formula. T equals 1 over F. Okay? Because like I say, they are the inverse of each other. Right? So what I want to do is find find the period of this rotation, knowing that this is a frequency of 830 revolutions per minute. Now, do I want my period in minutes or seconds? Okay, so can I figure out how many revolutions per second this is? What do I divide that number by? That's the number of revolutions in a minute. I want the number of revolutions in a second. It's divided by 60. Okay, so the number of revolutions per second here is 13.8. So this tire goes around 13.8 times per second. Is that pretty fast? That's really fast. Okay, so 13.8 rotations per second. So now I know that t equals 1 over f. So I just go 1 over 13.8. And that'll tell me how many seconds it takes to go around once. Okay, it's the inverse. Is it going to be less than a second? Way less, yeah. Okay, so if I go 1 over that, okay, so it takes 7.2 hundredths of a second for it to go around one time. Okay. All right, so now I have t and I have r, because the question gave that to me. So now can I calculate the speed at which this tire is moving? Right. So v equals 2 pi r over t. So 2 times pi times 0.29, the radius of the tire, divided by that 0.072 seconds. Whoops, not divided, times. Not times. I wanted divide. I took it away. Oh, sorry, not times. It's 0.29. That's what I wanted. Then divide by my answer. Okay, so 2 times pi times the radius divided by the period. Okay, so this tire is moving at 25 meters per second. Okay. Everybody okay with that? Now, I could also have changed this formula if I wanted to. Okay, t is 1 over f, which means f is 1 over t. They're the inverse of each other. Okay? If f is 1 over t, is this formula really just saying 2 times pi times r times 1 over t? So could I have just written it like this? 2 pi r times f? If f is 1 over t? Yeah. Okay. You can also do that and save you a step. Okay. Everybody okay with how that one works? Okay, so that's what we just did. That's the math of what we just did there. Okay, so for uniform circular motion, okay, the magnitude of the velocity vector is constant. That means it's a constant speed. Okay, it's not speeding up or slowing down. But what is changing is the direction. Okay, any change in velocity, even if it's just a direction, is still an acceleration. So this object is always accelerating. Okay, and to be accelerating, there has to be that force, a net force, and it's always directed towards the center of the circle. Okay, so centripetal acceleration is the acceleration of the object towards the center of the circle. Okay, so if you are moving in a circle, you are always accelerating towards the center. Okay, anybody ever ridden the Gravitron? Okay, they sometimes have it at the Calgary Stampede. It's the one you go inside it, it spins around a circle, and you get pinned to the wall. Yeah, okay, that's called the Gravitron. Okay, that works on this idea. Okay, you're on the inside of a spinning disk. It's actually how artificial gravity would be generated. If you ever watch, like in The Martian, they have the spinning part of their ship. Okay, it's just a big Gravitron. Okay, you're moving around and around in a circle, and you're pinned to the inside of the circle. It feels like gravity, even though it isn't. Right, so on the Gravitron, okay, you're pinned to the inside, and you can lift up your feet, okay, and you float. You don't fall back down. Because you're going fast enough that your desire to leave the circle in a straight line pins you to the wall, and the wall pushes you back towards the center. Okay? If that force is hard enough, it's enough to overcome gravity and you don't fall. Does that sort of make sense? All right. I found a video this morning of the Gravitron, so I'm going to show it out. But I can't. Right, so centripetal acceleration, okay, can be calculated with this formula here. Your centripetal acceleration is your centripetal velocity squared divided by r. Okay, so that means that as your velocity goes up, your centripetal acceleration goes up in what way? Linear or exponentially? Exponentially. V is squared here. Okay, if I double my centripetal velocity, the acceleration I experience quadruples. Okay? So very, very quickly, it takes a lot more force to hold you in a circle. Okay? This is why, okay, when you take a corner in a car, you have to be mindful of how fast you go. Okay, if you take like the exit ramp out here, right? If you take that at the recommended speed, you hardly feel anything. If you try and take that at twice the recommended speed, you'll slide out for sure, because it would take 4 times as much force to hold you in the corner as it did when you took it at the speed limit. Okay, and friction is unlikely to be able to provide 4 times as much force. Okay? In fact, we'll talk about it tomorrow. Okay, but those curves, banked curves like those exit ramps, are actually designed so that if you take them at the recommended speed, you would stay in them were they totally frictionless. Okay, they're actually designed that way so that they are safe regardless of the road conditions at that speed. Okay, now if you go slower than that speed, what will happen? You'll slide in. If you go faster than that speed, you slide out. Okay, I've actually seen it happen. I've seen somebody take a super icy corner after freezing rain too slowly. They were overcautious and they went into the middle. Okay, everybody else is sliding toward the guardrail, okay, because they're going too fast, and this person got overcautious and slid into the middle. Okay, it happens. Okay, now, so the relationship between speed and centripetal acceleration is exponential. Okay, what happens if the radius gets bigger? What will happen to the centripetal acceleration then? It'll get smaller. That's why you take a corner wider, right? We naturally just know that. If I take a corner wider, I'll be able to make it. Because as soon as I make R bigger, I'm dividing by a larger number, and A will get smaller. Okay? So the amount of force then needed to keep me in will be less because I took it at a wider radius. Okay? Everybody all right with that idea? All right, so centripetal acceleration is a vector quantity. It's acceleration after all, but it always has the same vector. Centripetal means towards the center. Okay, so it's always centripetal force, centripetal acceleration towards the center. All right, and then we got David and Goliath, but the video hasn't been working and I haven't been able to find another copy of it, but it's basically showing how David could have killed Goliath given just a rock and a sling. Okay, and basically what they found was with a simple sling, okay, he could have flung a stone with enough force that it would have hit Goliath in the forehead with 3,000 newtons worth of force, which is enough to shatter concrete. Okay, so as long as he could be accurate, which of course he would be because he would be using the sling to scare off predators from his flock of sheep, okay, he would have been able to hit a target like Goliath's forehead at fairly close range pretty reliably. Okay. So, lesson to be learned here in terms of strategy. Okay, so lesson learned strategically. You have a vastly superior military force. Should you agree to combat the enemy 1-to-1? No. You should overwhelm them by the sheer military superiority that you have. That's what Goliath didn't do. Now, in the end, he didn't want to kill all of the Jewish people, so he said, if I win, you all surrender. And then against the boy, so I'll win. And he thought he was wrong. Didn't work out so well. All right, we'll talk about that a bit tomorrow. If I can get everybody to wipe down your desks and everything, that'd be awesome.